How's it going, everybody? And welcome back to our Cisco Enterprise series. In this video, we're going to be taking a look at OSPF media dependencies and talking about how different processes work with inside of the OSPF domain, the interfaces, and things like that, so that we understand some of the specifics that come into that. So once we go through this, we'll be in a much better understanding of how OSPF handles things when it comes to interfaces, LSA types, that type of stuff. So without any further ado, let's dive into this bad boy. So OSPF's behavior changes depending on what type of media it is configured on. So Ethernet versus frame relay. Now we're only going to be dealing with Ethernet in our particular case, but there are some cases when we get into WAN related technologies and we start taking a look at point to multi-point and stuff like that with the network types over DMVPN, that we'll see a slightly different operational state when we start working with that. But the key point here is our main interface type will be Ethernet and not frame relay. So there are some older videos that I've recorded, I've mentioned this a few times already, that if you want to see what this stuff looks like in action, go back in time to some old content that I created, OSPF and frame relay, stuff like that, where I actually do demonstrate it, because at the time I was doing studying for those exams where frame relay was still involved. OSPF defined network types to deal with different network media characteristics. So the network types control are hellos and update sent, who forms adjacency, and how the next hop is calculated. There's a few different network types as well to go along with that. So we have broadcast and non-broadcast. These two right here are going to have a designated router and a backup designated router election process. Point to point, point to multi-point, and point to multi-point non-broadcast do not have a DR or BDR election process. So therefore, they will not have a type 2 LSA exchange. Network types and forming adjacencies. OSPF network types do not need to match to form adjacencies, but they do need to be compatible. Other attributes must still match, like the timers, stub flags. Are you stub versus non-stub, or are you totally stubby versus non-stub at all? What makes the network type compatible? Usage of the type 2 LSA. And that's one thing I want to make sure that we understand. If I use broadcast on one side and non-broadcast on the other, will it still work? I honestly don't know, because I haven't really tested that. I've always kept them synonymous on both ends of a link. But I do know for a fact that if I was to do point-to-point or point-to-multi-point, those will work. Because over DMVPN, when you want to start looking at OSPF over DMVPN, changing the network type will change how phase 1, 2, and 3 work with DMVPN. So, for example, I talked about this in a previous video, where if you set the hub as point to multi-point, and then you set the spokes to point on their network type, they'll form an adjacency, but it'll be from spoke to hub, but not spoke to spoke. But if you went point to multi-point on everybody, hubs and spokes, you'd be able to form a full mesh of OSPF adjacencies. So just keep that in mind. OSPF Type 2 LSA review. The Type 2 LSA is the network LSA, which is generated by the designated router, describes who is adjacent with the designated router, and is not flooded outside the area they originate in. It's used to optimize OSPF operation on a shared segment. So it's going to reduce the number of OSPF adjacencies, reduce the LSA flooding replication, and simplify the shortest path first calculation. Now, one thing that I did make note of here when I was probably going from CCNA to CCNP or whatever it was the network type compatibility. So broadcast and non-broadcast are compatible. Network types that do not use a Type 2 LSA that are compatible are point-to-point, point-to-multi-point, and point-to-multi-point non-broadcast. However, if you mix point-to-point and broadcast, this will not work. And I will demonstrate this to you at some point. I don't exactly know when I'm going to do that, but I will demonstrate that. Broadcast. So when it comes to broadcast, default on multi-access medias, so Ethernet and Token Ring, but Token Ring is so old it doesn't matter. Sends hellos and updates as multicast. So if you are doing point to point, you're going to send to 224.0.0.5 because there's not going to be a designated router election involved, so there's not going to be a DR. If you happen to be on a point to a broadcasted interface, you're going to send to 224.0.0.6. So whoever is the DR will be the router that receives traffic to 224.0.0.6. And, well, actually that's not true because 224.0.0.6 is always going to be a group. So these are group addresses. So you would be sending traffic to that. So the way that would work, the way that, let me give you a high level overview of how multicast works and the respect of how groups work. So the concept is very, very simple. If I have 224.0.0.5, actually, let's make that a 6 because that's actually what it is. So the group is what you send traffic to. So if in multicast, you're going to have the concept of a sender, and you're going to have the concept of a receiver. What you're going to do is the sender will be sending traffic to 224.0.0.6. The receivers are going to join the multicast group of 224.0.0.6. And what will end up happening is when the sender sends traffic to this group, but that is not what I wanted to do. Undo the last action. Can I do that? Oh well, I'll just redraw it. So we have 224.0.0.6. You have your sender and you have your receiver. The sender sends traffic to 224.0.6. The receiver joins 224.0.0.6. But when the receiver joins the group and the sender is sending traffic to it, the sender is actually sending information directly to the receiver. Now, where does this come into play? Well, this comes into play whenever a device enables OSPF on a particular interface, so a shared segment, as it's said multiple times already. What's going to end up happening is those interfaces are going to join 224.0.0.6 as they're going to join that group. So what's actually interesting about this is if you want to test multicast operations, routed multicast in your network before you go hand it off to the application teams, you can do the command IP IGMP join group. Actually, I think it's just the join group. And you specify the IP address of the group that you want to join. So 224.0.0.6. When you do this on a particular interface in the network, that's going to tell the router that you configure that command on to join that particular group. That's going to signal to the rest of the network, hey, there is a receiver for this particular group. What happens when you enable the network statement or you go to the interface level and you type in IP OSPF, whatever the process ID is, and then the area, you are going to have that particular interface that's tied to the network statement or IP OSPF 1 area 0 command is going to join the multicast group 224.0.0.6. Now, the reality of it is this. Whoever the designated router is, that's who's going to actually be joined to that particular multicast group. Because 224.0.0.6 is where you're going to send the update to. So if you take R1, you take R2, and let's say we have R3, and we have a LAN segment setting up between this guy, and R1 is your designated router, R2 is your backup designated router, and R3 is your DR other. What will end up happening is R3 there will be an update sent to the DR, there will be an update sent to the BDR. The BDR will then and the DR and the BDR will then send updates back out and to every other device on the network. But when they're sending these updates out, they're sending them to 224.0.0.6. Now, if you don't have any other devices and you have flipped over to point, then the process is there's no DR BDR, and you would never have R3. You would just have R1 and R2. So they would both join 224.0.0.5. By doing that, actually let's back that up a little bit. By doing this, they're both joining the same multicast group, which means this one's going to send to this one's going to send to that. They're both going to receive messages. So when we go through and have that configuration in place, now you don't have to do anything. It automatically happens behind the scenes. That's essentially what's going to end up happening here. And then when that process happens, when you probably saw it in the Wireshark output, you would send to, say 10.1.2.1 sent to 224.0.0.5. And then you would have a response, like let's say there's an LS link state update. Well, that link state update would get sent from R1 to R2, but it would be 10.1.2.2 sending to 10.1.2.1. Whenever you're doing an update, you're sending it via unicast, and then you're good to go. But any hellos, stuff like that, updates and things like that, they're going to be sent to the routes themselves are going to be unicasted and stuff like that. So that's essentially what you need to remember in terms of how OSPF processes this. So in the event, and I don't want to get, I feel like I'm beating a dead horse at this point, but that's the concept. As soon as you enable the interface to send and receive OSPF hellos, the interfaces themselves join the multicast group. And when they do that, they're able to send to the 224.0.0.5 and accept the multicast, the OSPF hellos. So by doing that, by joining the group, they're able to send hellos and they're able to receive hellos. And then when there's an update, they unicast it back. So just keep that in the back of your mind when you're trying to understand how OSPF processes things. So this will make more sense when we get into multicast and you actually get to see it firsthand. If you've never seen multicast and you're like scratching your head trying to wrap your head around this, I would say probably don't try to lock this particular concept down. What I would say more specifically is just know that the well-known link local multicast group for the designated router for OSPF is 224.0.0.6, and the well-known link local multicast group for all SPF enabled devices is 224.0.0.5. If there's no DR, if you're using a point to any type of network type, that you're going to be using 224.0.0.5 because there is no DR. For those of you that are like CCNA, CCNP level, that's where I want you guys to kind of lock down your understanding. So let's continue moving forward. Non-broadcast. We have IP OSPF networked non-broadcast, default on multi-point NBMA interfaces like Frame Relay and ATM. Sends hellos as unicast, manually defined addresses with the neighbor command. We're not going to have to really deal with this too much. But in the narrow likelihood that you're ever going to run into a media type or some sort of transport that doesn't support multicast, the neighbor command will be necessary in order for this to work. So let's go ahead and talk a little bit about the DR operation. So used on, again, broadcast and non-broadcast links. So, forms adjacencies with all routers on the link, listens for link state updates on 224.0.0.6, minimizes adjacencies, minimizes LSA replication, receives hellos, then sends updates on 224.0.0.5. Does not modify the next hop value. Technically, the DR can be the router you are on. OSPF, like ISIS, treats the DR as a separate pseudonode, which it must consult before computing SPF. Therefore, the router must ask the DR who it is adjacent with and what its cost calculation is to its adjacent neighbors. The BDR, used for redundancy of the designated router, but does not flood LS updates. The DR other, all other routers in the link. Forms full adjacencies with the DR and the BDR, stop at two-way adjacencies with the other routers. Can it go full adjacency at some other point? It can. If the designated router were to fail for some reason or not be reachable, and then another router is elected the DR, then it would automatically form a full adjacency with that device and continue its operation. So let me come down here. This is probably going to be a little bit more. Okay, we're almost there. So let's talk a little bit about the election process. The DR-BDR election process is actually very, very straightforward. It's based off the following. Out of the gate, it's going to be a priority, 0 through 255, higher the better. By default, everybody's going to get a priority of 1. So if you don't want a device to ever participate inside of the DR-BDR election process, you can set the DR priority to be, or the OSPF, I think it's IP OSPF priority 0. Now, if they are all the same, right, what will end up happening is you'll choose the, whichever IP address is the highest on the link, that will become the DR. So when it comes to the router ID, highest loopback or interface IP address can be statically set, the higher the better. Use the wait timer to stop preemption of current DR-BDR. So what that means is, unlike and we haven't talked about ISIS yet in the designated intermediate system, an order of operations can preset the DR if you want a specific router to be the DR. You need to have the priority set to not elect a router DR-BDR, so you'd go to a particular device and you'd use the IP OSPF priority 0 command. If the hellos are sent before other routers send the traffic, the first router will be the DR. So essentially what that means is, if you want a particular router to be the DR and you go slowly enough, which doesn't take a whole lot of time, you're talking like 40 seconds. You go to device A that you want to be the DR and you type in IP, or you enable OSPF on that, and you could even bump the priority up to 255. 255 guarantees it to be the DR, assuming that there's no other devices with a priority of 255. And then go to another device after the wait timer is expired. Once the router elects itself as the DR, you go to any other router and enable OSPF on it. It will automatically elect itself as the backup designated router and then work its way down. So what will end up happening is, if you take your time with it, you can basically guarantee which device is going to be the DR. If you don't, then you're running the risk of whatever device you on the network will become the DR. If there isn't full layer 2 connectivity, LSA replication will only happen between directly connected neighbors. When OSPF sends an update to its neighbor, only that neighbor gets it. Multicast and unicast for OSPF have a TTL of 1. Broadcast is sending updates as multicast to 224.0.0.5 and 224.0.0.5. Non-broadcast is sending updates unicast. So you'll send the updates via unicast to the DR. And then the DR will then unicast those to the specific neighbors that they need to update. So remember, everybody forms an adjacency with the designated router. So they'll multicast the updates to 224.0.0.6, and they'll then, from the DR's perspective, he unicasts the updates outbound to whoever the respective neighbors are that need to get it. Point-to-point, how do you set it up? IP OSPF network point-to-point. Default on point-to-point medias, HDLC, and point-to-point protocol. Sends hellos as multicast to 224.0.0.5. No DR-BDR election. Supports only 2 neighbors on the link. Timer intervals can be configured. Hello 10, dead interval 40, wait 40, retransmit is 5. Point-to-point, or point-to-multipoint. Treat the network as a collection of point-to-point links. Sends hellos as multicast to 224.0.0.5. No DR-BDR election. Special next hop processing. the next hop value is updated to the interface IP address of the hub. Usually the best design for partial mesh NBMA networks, like a hub and spoke DMBPN network where you don't require spoke-to-spoke communication. So again, the hub will be configured as the point-to-multipoint network type, and the spokes will be configured as point-to-point, because they're going to be forming a connection directly with the hub. Point-to-multipoint non-broadcast. There's your command right there. Same as point-to-multipoint, but sends hellos as unicast. Manually define addresses with the neighbor statement. Allow on a per virtual circuit cost over OSPF cost over NBMA. Virtual circuit implies frame relay. There is no DR/BDR election. Next hop processing is updated. The next hop is going to be the IP address of the hub. So simply what that means is, and I'll draw this out real quick for you. If I have R1 as 10.1.1.1, and I've got R2 and I've got R3, and I've got a LAN segment going out. So they're all the same subnet, but it would make more sense. Yeah, they're all the same subnet, because I'm like, well, wait a minute, point to multipoint, they'd have to be. If you're point to point from R1 to R2 over a tunnel, a single tunnel, and where you would do this isn't at the Ethernet interface, you do this at the tunnel level. So let's assume that actually, let me back this up a little bit. I've got a DMBPN cloud, and we haven't really talked about DMBPN yet, but we've got, this is all attached to tunnel 0. So tunnel 0 here has 10.1.1.1. R2 has tunnel 0 created on it with 10.1.1.2. And R3 has tunnel 0 on it to 10.1.1.3. What you would do is at the interface level for R1, you would go and set the network type as point to multipoint. So it would be IP OSPF network point to multipoint. You would apply that command to right here. So let me go back that up real quick. This would be point to multipoint, and then you go to the tunnel interfaces on R2 and R3, and you would set these guys to be point to point. Now when they do that, they're going to have a next hop process set to 10.1.1.1. So what's going to end up happening is there's going to be basically a route. I'm putting a default route in there just for basic understanding that says if you're trying to get to anything, point to R1. And then this guy will do the exact same thing. There will be a default route that will point to R1. What will end up happening is your next hop will be R1's tunnel interface address. The caveat here is we may or may not be able to get routes between spokes. So if you have a need to go between spokes, right, spoke to spoke communication, then that's what they refer to as, so DMBPN phase 2 and phase 3 both support that. We'll talk about both. But the reality of it is, if you want to do that, then you're going to more than likely need to go point to multipoint everywhere to do a full mesh. So this would actually get converted over to, it wouldn't be point to point here anymore, it'd be point to multipoint. But again, your next hop for everything from the spoke side, doing point to point as a network type, would be 10.1.1.1, which is going to be R1's tunnel interface. That is how that works. And last but certainly not least, we have the loopback. Special case for loopback and looped back interfaces. Advertise a link as a /32 stub host route, where if you type in IP OSPF network point to point, use to disable this behavior. So what will end up happening is it'll advertise it as a /24 and not as a /32. So if you put in a /24, it'll, before you type this command in, if it's a /24, it'll advertise it as a host route. If you wanted to honor the subnet mask, do the IP OSPF network point to point, and you'll get your /24 route advertisement. So that is it for media dependencies. So you probably heard me sound like a broken record a little bit, but I really want to hammer these points home and make sure you understand them. So that is the key thing that I want you guys to understand in terms of the day-to-day type stuff. So if you guys have any questions or concerns, comments, stuff like that, please drop that in the comment section below. If you haven't already done so, please like, share, and subscribe, and I'll catch all of you fine folks in the next video.